So CFD is basically a tool by which we have a qualitative and quantitative prediction of fluid flows, any flow phenomena for that reason. So therefore, I would rather term CFD as computational flow dynamics than just fluid dynamics. Please don't limit yourself to just fluid dynamic studies. We can analyze any phenomena where there is flow involved. First of all, we need to have the mathematical model clearly defined. Once we have the mathematical model, we use some numerical methods to solve the governing equations. That's usually partial differential equations in integral or differential form. When they are solved using numerical methods, using some software tools involving different steps, we end up having a nice setup for analyzing and parametrically studying several design points, several geometrical designs as well as operating designs. So in short, CFD is the science of predicting fluid, heat, or any other transport phenomena by solving the mathematical equations which govern these processes. And we are using a computer which has a often it's a software which runs on a computer which has these equations being solved using numerical methods. So that's the usual procedure. We have the geometry being built up. Let's say it's a flow through such a bend, and we have the problem set up. We have the geometry being defined into smaller fragments, being broken down or segregated into smaller fragments. That's what a mesh is. So what we are doing actually is defining some probe points where we want the analysis to be done, and we define the boundary conditions which make the solution inside the domain unique. And once we have the boundary conditions defined, the problem set up, we actually use a computer to solve this problem. So computer's role comes here. And ultimately, of course, we want to visualize the results. We get a lot of data points and at all these probe points, but just the numbers will not make sense for us. Therefore, we try to use some visualization tools to analyze the results. So CFD is overall is a three-step procedure. Actually, CFD consists of pre-processing step where we define the geometry, where we define what my domain of interest is, and this domain is of course afterwards broken down into smaller fragments. That is what a mesh generation step is. I'll take you through some examples which will define this mesh. We set up the problem, that's boundary conditions. Once the problem has been defined, we ask the given software on the computer to solve it. We can very well do it also through hand calculations, but it will take a long time. So therefore we have different software packages available for doing this task for us. That's solving the equations. We can include additional models as required by the physics, and the numerical methods are also defined at the solver stage, and we are solving the whole problem. Once we get the numbers, we get all the values at different probe points, we are analyzing them through color plots, contour plots, through appropriate graphs, graphical representations, or let's say we have also specific numbers like the drag force or the lift force, how much quantitatively is the heat transfer occurring, and subsequent to this we can also derive numbers like Nusselt number which define heat transfer coefficient for further analysis. We can generate reports. That's the analysis part. So we have a three-step procedure being defined in CFD. So basically what numerical simulations help us with is quite very many advantages. We have people using it in building designs. Uh, we have a lot of analysis being done at the biomedical sciences level for finding out if arteries will converge, if there is a deposition of some kind of plaque inside an artery. Or we have also people using it in the weather forecasting industry, and of course for a lot of building designs, heat transfer or heat ventilation, and a lot of analysis as far as that is concerned for air conditioning applications. We have chemical engineers using it of late for the last 20 years or 15 years or so, and it is really making a lot of mark. We have even open source solutions available now dedicated for chemical engineering applications. So we have applications in aerospace. We can see it can primarily be used for internal flows as well as external flows. So these color plots, you must have gone through them several times. So we have in aerospace industry, which is actually the bread and butter for CFD. computational fluid dynamics has been used in aerospace industry for a lot of, for I mean actually I can say more than the last 60 years or 6 decades, and it has been used in a variety of fields for combustors, for inside the cabin, around the airplanes, around the wings, around the fuselage, around the tail section of the airplane, for helicopters. There's been a lot of applications in aerospace industry. In automobile industry, again, it's more of a blunt object that we are usually dealing with. So there's a lot of pressure drag, form drag, but again, internal cooling for passenger comfort is also another part that we try to analyze in automobiles. And a very important part is underhood thermal management. That's a very important field. Again, we have the engine simulations being conducted for automobile applications. So automobile application is another field where CFD has great role to play in nowadays time. In electronics, we have applications for data center cooling, we have applications for PCB cooling, or we have heat sink performance being analyzed. We have applications in heat ventilation, air conditioning in rooms, in cabins, for duct design, again, very many applications. So let's focus now a little bit more specifically on how CFD works. We'll take up some examples how CFD can be used for implementing it on real life problems, for analyzing real life problems. Now this is the geometry of a pin-fin heat exchanger, which is typically used for transferring heat in radiators or in household applications in countries where heating is part of a room. You cannot really neglect heating. So we have there such fin tube heat exchange. So we have hot water often being poured through these tubes. In some other cases, we have cold water being passed through these tubes. We have cold water being poured through these tubes, and we have hot air being blown on it. So that's a typical fin tube heat exchanger. And what we'll do in CFD now is to say, if you see this whole problem analytically, it's quite hard. Of course, people have come up with correlations based on a lot of experimental studies that they can perform a lot of analysis at the experimental stage along with some analytical studies. But as far as simulation is concerned, we'll see that we'll be taking only a part of this geometry to do a simulation. There's a commercial fin tube heat exchanger. We take a small section of it. You can see maybe it's a bit hard for you to analyze how this would represent this geometry. Of course, it's just a passage that has been taken between two fins. The very small fins that you see here, we've taken a part of it, a half section of it, and we have the fins attached to the tube. So we'll see that we are going to do a simulation, we are going to do an analysis of the system. What we do is we first of all jot down what the conservation equations are for mass, momentum and energy, because it's a heat transfer analysis. Of course, it's not just the flow of fluid and the momentum equations that we need to solve, but also the energy equations. We try to simplify the problem, which is what we have done, by reducing the extent of the problem. We try to ask ourselves whether we can do a steady state analysis or do we need to perform a real unsteady simulation, whether the flow is compressible or incompressible. Now if it's a very hot air which is being passed through this system, as you can see here we have flue gases which are flowing into this between the two fins. The temperature variation is quite significant and does vary the density of the fluid, so it is to be taken into account. And we'll be seeing how heat is transferred across these fins into the tube, in which there is a cold water flowing. So these are the boundary conditions we need to define entirely a given problem. We can see this is the step where we take the geometry and start dividing it into smaller fragments. This is called meshing, the pre-processing step, the grid generation step. We divide the geometry into smaller fragments. We end up having the mesh where the equations will be solved, not the exact integral equations, but converted into a discretized form of the equations. The geometry is discretized and so are the equations discretized. And these discretized equations, when they are solved, we get values, which using a visualization technique we can generate such nice color or contour plots, which can really give us a good insight into where the hot areas are, where the hot spots are, where the cold area is. And it's not just the qualitative depiction of the values that we have generated, but it's also something to do with the numbers. You can see the numbers. We can see the temperature varying from something like 464 Kelvin to 361 Kelvin in this figure. So we are also getting quantitative numbers which can help us to analyze the overall flow phenomena. Now if we analyze it from this view, from the view into between the fins, so between the fins you can see the fluid is uh, passing further, is moving further, and the temperature is also varying according to this. So we have the temperatures varying in this area, and we have area where the temperatures are quite high, which is typically encountered for flue gases, and reducing as it moves into the domain. Very rapid reduction of the temperature. That's another example in which we have a cascade of tubes placed inside a domain across which water is being poured over it. So it can be a physical system in which, say, we have a cascade of tubes. Now what we do is, again, we are trying to show you how we can simplify our problem. We have a whole complicated setup of several cascades. Now to start with any given simulation, we would not actually start doing it on the real problem. What we would end up often doing is we try to take a smaller section of this, try to set up the problem, try to gain confidence in simulation, and then actually implement it. If the computational resources and the time permits, we will end up doing simulation on the real geometry. But as you can see here, we have taken only a section of the geometry. Again, what you can notice here is that we have generated something called a mesh, which is discretization of the geometry. In this case, what you can see here is like we have a nice boundary layer. You'll get familiar with these terms as the course progresses. Just you can see that we are interested in capturing the flow phenomena, especially around these tubes, the cross section of the tubes that you can see here. And we have the overall system being modeled. We set it up on a software like Fluent. Now that's an old version of the software. We will be teaching you more on the 12.1 release later on, but you can see this is what a usual setup looks like. We set up the whole problem, we set up the boundary conditions, we define how the flow is to be analyzed, what all specific quantities we need, and once we have this information, we get such nice results like these. Now what you can see here is the temperature variation around these cascade of tubes. You can see there are regions around the tubes which have a lot of recirculation. That's where the heat starts building up. We have the cold stream going around it, and the tubes are having the hot water inside. So you can see very nice depiction of the real life situation through a two-dimensional analysis. And this was performed in ANSYS Fluent. On the bottom you can see that a single so to say such a tube was analyzed for a phenomena called the vortex shedding. Now that is typically encountered for flow around such tubes because of disturbances and a very familiar process called the von Karman vortices which are generated. You can see a lot of vortex shedding, according to which you can see that this tube encounters a lift force which is very sinusoidal in nature. Now this was performed in ANSYS CFX. You can see the lift force variation with time. This is simulation time on the x-axis, and we have the lift force on the y-axis. It has a clearly sinusoidal behavior. So you can perform such very nice post-processing in CFD tools which are available. So overall we can try to summarize what advantages we have in CFD. So we have advantages in CFD as far as the low cost is concerned. It's rather the software and the manpower which is limiting in this regard, but usually you can reduce a lot of experimental studies. In this way you reduce the cost of your analysis. We speed up the process because we are using fast computers. It's possible nowadays to perform actual simulations on desktop computers or on laptops. We are actually able to simulate real conditions. Now, earlier in experiments, when they were thinking about hypersonic flow of a re-entry vehicle back into Earth's atmosphere, we're dealing with Mach number as high as 20. Now, it's not possible to actually perform an experimental study of such a system on under normal conditions. Any wind tunnel cannot actually produce a Mach number 20 value. So we have to rely on CFD simulations, validated and stable and accurate CFD simulations, which can actually simulate such real conditions. So you can really theoretically simulate any physical condition as long as the mathematics is defined. We can also simulate ideal conditions, and we often end up having a comprehensive information, not just at limited data points, limited probe points. When we are dealing with advantages, we have to be also aware of some limitations of CFD. Now, CFD has two kinds of errors, I would say. Two kinds of errors. One error is called the modeling error or the physical modeling error, and the other type of error is called numerical errors. Now, these are the limits which are placed on CFD and reliability of CFD results. The physical modeling errors usually arise because of lack of expertise on the part of the user, lack of ability on the part of the software to include specific physics. So when the mathematical model is not well defined, when the physics is not well defined mathematically, that's where we have problems as far as the physical modeling errors are concerned. If we can mitigate these things, if we can get rid of these mathematical modeling problems, if we can capture every phenomena appropriately through mathematical means, we are done with this mathematical modeling errors. Sometimes we also have modeling errors because of wrong boundary conditions, which you would come across when we deal more in a profound way about the software fluent, that the boundary conditions are often the ones which give a unique solution to the problem inside the domain, inside your computational domain. So if the model is not well defined as far as the boundary conditions are concerned, you're bound to have errors also in that case. As far as the numerical errors are concerned, there are two types of numerical errors. One because of the computer, which of course we are not um, very much in control, because computer has limited precision. It does round off some decimal points. It can only store data up to some decimal points, and therefore we have some round off errors. More often than not, this round off error is quite insignificant compared to the kind of insight we obtain through CFD simulation. So numerical errors, as far as round off errors are concerned, because of the computer, that's not really a significant contributor to the errors that we are going to usually encounter in a CFD simulation. Truncation errors, that's because of the numerical method. Let's say we define the solution of a problem using a numerical method. A partial differential equation is being broken down on a discretized geometry in a discretized form. There are some uh, orders of accuracy that we obtain by either neglecting certain terms for the sake of simplicity, and in the process we end up having some truncation errors. Now, when these truncation errors do play a role is when we want enhanced accuracy. There, the truncation errors have to be reduced to as much extent that we can manage. Truncation errors do have a role to play, and that's as far as the numerical method is concerned. That's where the software can try to improve it. So the software that we'll be using, it should be able to reduce the truncation error to the limit that it's possible. And in this way, we can actually get rid of truncation errors as well. In some cases, also at the level of the user, we can try to refine the mesh and get a very fine mesh, which can help us to get a very good result. And beyond a point, of course, the solution becomes independent of the mesh. That's when we say the truncation errors have been completely um, ruled out, and it's only the round of error that we are facing. In terms of real life simulations, you can be aware of it, that the software can often take care of the truncation errors, can often take care of the mathematical modeling problems. So it's just at the level of the user that should be able to include the appropriate physics, use the appropriate numerical schemes to get rid of these errors. The user's expertise will come to understand, to appreciate these limits and how to find solutions to them. That's why through this course, we would be able to help you out to figure out where you can reduce such errors. Errors can also be at the level of boundary conditions, as I mentioned. This is a simple flow through a backward step problem. You can see here we have a uniform inlet, and we have um, a fully developed flow which is a better approximation for the inlet conditions. So overall, to summarize, CFD is a powerful tool and it can be used for a lot of heat transfer flow analysis. As far as the analysis is concerned, CFD can help us to perform a lot of parametric studies, lot of studies on different kinds of geometries. Usually, the cost of CFD has been decreasing with in the recent years. That's primarily because CFD has been accelerating the growth in the hardware industry, and because of which we have very fast desktop computers available nowadays for performing a lot of simulations, and this can help us to perform multiple simulations, a lot of parametric studies, and CFD has a major role to play in the coming years. So I hope you enjoyed this lecture. We'll be following it up, following this lecture with a demonstration on how CFD can be useful for you through a demonstration. In addition to this, you can please try to answer the questions on the assignment which have been provided along with this lecture, and you will be able to find out how much you have found, how much you have gained from this lecture. And I hope you enjoyed this lecture. Stay tuned for the subsequent lectures which are going to follow. Thank you very much for your attention.